Okay, Sheikh Ali, how are you?
You know, the meaning of Sheikh in Arabic means Louis and Yemen.
It's a good name, right?
Yeah, it is the KIB appears.
Exactly what I feel you were saying. And I'm so proud of you.
Like this.
All Yemenis are Farsi.
This is the issue here. That's why they are fighting together. All the problems.
Yes, all every problem.
What like hand?
Except NMR. Okay. So, how do you feel, Pakistani students, that you are sitting between so many Shio from different countries? It's called Shio. The plural of, so not so bad. Huh? I have in my team in Comsec, we have people from, we have staff from Mauritania, who's my chef, Zainal Mustafa. Then I have someone from Senegal. Then we have someone from Gambia. Then we have someone from Benin. Yeah. And then we have someone from Gabon and Somalia. Sudani is going to join us. And Nigerian is coming. Bangladesh is already there.
Arabic.
No one from Yemen.
Arabic. Egypt.
Egyptians are so expensive to be hired. Right? Again. Assalamualaikum. Good morning. Anyway, let's discuss NMR spectroscopy. Shahida. Assalamualaikum, everyone. Okay, Bismillahirrahmanirrahim. So, you see, we have actually moved from one-dimensional domain to two-dimensional. We have been so absolutely lucky that we have, to some extent, understood what one-dimensional spectroscopy to the core. And then we are moving on two-dimensional spectroscopy we discussed last time. And what I was trying to say that largely the domain, the reason for two-dimensional spectroscopy was not sensitivity. Sensitivity is not the driver for 2D. The driver for, you understand driver? The main key reason for NMR spectroscopy to eventually evolve back in 1970s into two-dimensional NMR spectroscopy is this problem that they have faced in the interpretation of complex particles. You know, when they see a very complex single-dimensional NMR spectrum, they said, good Lord, we cannot really use it because it is not interpretable. So interpretation is a problem. And rightly so, because if you have in front of you an NMR spectrum which looks so horrible, like this, then it actually stops your capacity to understand. So someone named Gina, Jener, from the California Institute of Technology, he came up with a very interesting idea that if we can convert one-dimensional NMR spectroscopy into another domain, into two-dimensional NMR spectroscopy, then it becomes easy to interpret. And his idea was a very simple idea, which was that if you consider them as mountains in front of you with so much of overlapping, you can very well imagine that these peaks are not really single. You know, there are so many peaks behind each other. They are overlapping peaks. So overlapping is so much that despite the fact that all the information are there, you cannot interpret. You know, you have integration, you have coupling, you have chemical shift, everything, but you cannot interpret that. And that was the key reason they said, why don't we just see those peaks like mountains from the top? Overview, from above to the down. And to that, you need to add another dimension. That is the beginning of a two-dimensional mass spectroscopy, which has been a new chapter in NMR spectroscopy. Think of it, if it was like this, there was no way you could use it for proteomics. There was no way you could use it for structural biology. You know, there was no way you can use it for complex molecules, which are huge and all that. It's absolutely. So, all of a sudden, this field got open for many, many other disciplines because two-dimensional NMR spectroscopy was introduced. And once you have a second dimension, it's so easy to have third dimension, 4-dimension, 5-dimension, 6-dimension. I'll tell you what these are. Now, question was how to do that. That was a major question, how to introduce the second dimension. And this fundamental question of how to do that was later solved by two-dimensional mass spectroscopy. Let me remind you that one-dimensional mass spectroscopy is that you have your magnetization vector. You bring it to the XY plane, transfer magnetization vector. You may have as many pulses as you wish, but then as soon as you bring it to the magnetization vector on XY plane, you turn on the detector and you detect the signal. You have FID, you convert FID into frequency. Yeah? So even if you are recording 400 experiments, they are all exactly the same. Why you're recording 400? Because you want to have improved signal to noise ratio. Over there, the objective is sensitivity. The difference between one-dimensional NMR spectroscopy and two-dimensional NMR spectroscopy is this beautiful concept of evolution. In one-dimensional NMR spectroscopy, my apologies, you don't have this, right? You just have preparation, detection. Okay, no issue. In this case, you have introduced an evolution period. Now, why the word evolution was used? Evolution is a beautiful concept in biological sciences of changes with time, isn't it? So, in NMR spectroscopy, the change with time is detected. Okay? And what changes? Spins, right? So how spins change with time is recorded in two-dimensional. And why is it called two-dimensional? Because number one, you have this famous detection period, which is FID. right? This is one time domain, isn't it? And this is evolution time, which is also a time. So you have two times. And when you convert two times into frequency, you have two frequencies. And when you have two frequencies, you get two-dimensional energy. Okay? So this is basic fundamental architect morphology, anatomy of two-dimensional mass spectroscopy. But think of it, what actually happens during evolution period? That is the second question. What actually happened? And it's so obvious that when you bring magnetization vector on xy plane, then you don't expect that to be there forever. There are two things. Number one, that they have to go back, right? Forget that at this time. You don't want to confuse yourself. You don't want to confuse this T1, T2 relaxation because that is happening always. You know, that you cannot avoid. It has to go back. But during that very short span of period when they are on XY plane, reasonably well, detectable by detector, what happens? For instance, if it is a doublet, right? Split into a doublet, move away from each other. One is fast moving, the other is slow moving. And it's time dependent, isn't it? If you record FID exactly when you give a 90x pulse, you see them together. If you record another experiment, after some time, you find them away from each other, right? If you record third experiment with more delay, then you find them even farther than each other. When you record another experiment, you see them farther away from each other. When you record another experiment, you find them coming closer to the other side, right? And then eventually you see that when you record FID, you find one signal like this, then 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 up, then up, then up, then down, till it goes up, goes away from detector side. This is exactly what is happening right now. So you see, this is evolution time. And evolution time is named as T1, small T1. So never confuse this small T1 with big T1. Big T1 is your relaxation time. Never ever confuse it with that thing. It's all is a different domain, right? So this evolution time, Tina said that in this evolution time, these spins are moving away and combining them together, then again moving away, then combining them together, then moving away, then combining them together, till they go out, right? So for instance, if you record an NMR spectrum with T1 as 0 second, your first spectrum, okay? Then you record another experiment with T1 as 1 second. Then you record another experiment with 2 seconds, 3 seconds, 4 seconds, 5 seconds, right? When you record it, you know exactly that during this evolution time, magnetization vector will not be the same place. And therefore, FID will not be the same, isn't it? The FID of 0 T1 is going to be different from FID of 1 second T1 or 2 second T1. Is exactly if I and Adil are together in a football match, okay, and we move together with our balls. You click us, you get one photograph. This is detection, okay? And then after some time, I give him the ball that he moves away. After some time, you take another photograph. You'll find him somewhere else. You'll find me somewhere else also. And after another period, you find him away and find me away also. And during this time, during this evolution time, magic happens. You let them talk to each other. The transition vector, depending on the design of the experiment, talk to each other. And these exchange of information takes place. Like gossiping. Okay, you like gossiping. You gossip. You all gossip. In fact, you will gossip more than anything else. Okay. You're all a spins. If you get more time, you gossip more. If you get less time, you gossip less. You gossip more, you have more information. Isn't it? You're happy with this, right? So during evolution time, I'll bring in one experiment. I don't let you gossip. Again, I detect you. Okay. In the second, sir, you're so impatient. Can you allow me to complete my sentence? I would be honored. Okay. After some time, another experiment, you let these girls gossip each other more than that. This is one experiment. And then every time the information content is going to be more and more, depending on how much time you give. This is an evolution time of gossiping. I think gossiping is a wonderful word. We should call it gossip dementia in our society. This is proton gossiping, proton carbon gossiping, proton gossiping in long range. You let them gossip from 1 to ends. Okay. So where they would use not only word but also sign and gossiping. And I'm telling you, one of the most important experiments in NMR spectroscopy, the first sequence is called gossip. Okay. Somebody thought about it. Chief, over to you.
Excuse me, about I have confused it about the Harris T1 time. Okay. Before we take the T1, we take doing the 90 pulse to 100 pulse. What? That means I have 2 times now. How you make all this period between 90 pulse and 100 pulse? This is time. After 185 pulse, I have for this reason. But you make it all.
That's a very good question, honey. Yeah. I think the simple answer is you kindly forget this, please. Consider this as my mistake. This is 1 T1 time, and this 180 is a spin equipulse. Remember I told you that during the experiment there is a lot of divergence, not because of the actual factor, but because of magnetic anisotropy. So that 180 pulse is actually a spin equipulse. Okay, but this is the T1 time. There is no 2 T1 times, 1 T1 time. All the way through from 90 to detection is 1 T1 time. Okay, this 180 pulse is just for removing the effect of magnetic anisotropy. You're okay with this? Happy? Okay, so Who are you? I don't understand. Professor Dr. Ati, I believe from sound I can hear. So, I remember this famous pandemic period. आप क्या पूछ रही हैं मुझसे?
सर वहाँ पे अभी यहाँ पे नया समोसे सेट करवा दें आपने कहा
कोई अभी सीरियस डिस्कशन शुरू नहीं हुआ, आप समोसे पे आ गए। थोड़ा सा तो काम करें। Let me work. She's asking me whether we can have tea or coffee or something like that. I said, let me discuss a bit. I just started. Okay, anyway, so but I now come to a very, very interesting part of it. After every experiment, you record FID. Every FID is converted into a frequency. Okay. So if you have 400 experiments with 400 different event times implemented, you would have 400 frequency signals. Okay. If you put them together like this, one after the other, is called transposition. I remember that someone was giving me an example when I was in Cornell. They says, okay, record that on a plastic sheet. Okay. Then the second also this plastic sheet. Then plastic sheet. Stand them together one after the other. These frequency signals are different because of what?
The time.
Yeah, evolution time, nothing else. They are varied, they are different from each other only because of what? T1 time. Okay. So it's called transposition. So what you have done is that you have put these spectra one after the other till the end. They represent 400 experiments, 400 FIDs, 400 Fourier transformation, and 400 peaks. Okay. And now you come and move yourself like this. You see all these standing spectra. And when you see them, you would see like this, isn't it? You would see that slowly going away up, right? So this, if I say, okay, honey, you make a line on top of, make a line on it.
That's the only one. If I make it one line.
Yeah, one line. Right? Isn't it a pseudo FID? Isn't it like that FID? Right? But this FID is not a real FID. It's a pseudo FID. You created FID based on frequency spectrum. And that FID represent evolution time. These spectra are different from each other because of T1 time. Right? And now you get something like this. This is a pseudo FID. There is a special word in NMR spectroscopy which is called interferogram. Interferogram. Okay. Pseudo FID transposition of it all takes place by computers, right? FID, these frequency domain spectra are transposition, and then you get pseudo FID. Now the pseudo FID represent T1, right? You convert T1, you get another frequency. So you know the mechanism of it. One frequency coming from detection time. The second frequency is coming from this pseudo reconstruct. It's called reconstruction. You have taken frequency spectrum, you put them together, you created a pseudo FID, you converted that pseudo FID, and you got another frequency domain. This is the construct, and this construct could eventually give you a spectrum like this. One frequency and second frequency. Okay, you converted one frequency is based on detection. The second frequency based on evolution time. Two frequencies. You remember? Time is converted into frequency. In one-dimensional spectrum, there was only one detection time. There was no other variable. In this case, you have T1 also. And because of T1, there is a variable. Right? And that variable time is converted into frequency also. Two Fourier transformation, two time domain, two frequencies. Okay? And therefore, you get so many spectrum. You can have scalar couplings like cozy, toxy. You can have heteronuclear, mononuclear. You can have through space coupling, which is called dipolar couplings. You get nosy and others. And this is the most beautiful thing happened in the history of NMR spectroscopy. So you get spectrum like this. I told you that this is cozy correlated spectroscopy. You get J-coupled, in which you have coupling constant you can measure of every spectrum. For instance, this is one, carbon number one. Sorry, this mistake has never been correct. This is carbon number one, the most downfield carbon. It will appear as a doublet, right? CH. CH will appear as a doublet, right? So this is CH, and you can measure the coupling constant. So this is the frequency domain. C2 is also doublet. C6, where they say 6 is here. A pair CH2 will appear as a triplet. C4 CH2 will appear as a triplet. C5 will appear as a doublet. C7 will appear as a doublet. C8 will appear what? CH3 will appear as what? Quartet. And C9 will appear as the quartets, right? So you can calculate J-coupled. They're called J-coupled, right? Now, see, what I wanted to tell you that during this evolution time, you design your experiment as you wish. You can design experiment in which you only let proton talk to each other. You can design experiment in which you can have proton carbon talking to each other. You can design an experiment in which you have proton and protons talking to each other in a long way. Depending on your own choice, you can design experiment. During that evolution time, you let people gossip. You let these spins talk to each other. And I can design experiment for you also. If you are all a spin of a protein, okay? Some of you are carbon, some of you are proton. Okay, so one experiment. I said, okay, only proton will talk to proton. I don't bring you to XY plane. Okay, you're out. And only proton will talk to each other. Another experiment, I'll bring protons and carbons together on XY plane. I'll let you talk to each other. You get another aspect. Okay. You can also have, okay, I can design an experiment in which I don't let you speak. So you see each other only. There's a different set of information. In one experiment, I bring you with closed eyes and I let you speak to each other. You have a different set of information. Okay? So you see, exactly in the same analogy, hundreds of experiments were designed, hundreds of experiments, in which NMR spectroscopists designed a special experiment to extract special information. Because the question was the interpretation. If you would like to see that very extremely crowded, horrible looking photon spectrum interpretable, you develop a COSY. In COSY, you have another dimension and you can have correlate them. You want to see proton carbon, you have heteroCOSY or HSQC. If you have proton talking to each other, then you become nosy. And today I'm going to show you my most favorite experiment. Yes, madam?
Sir, I always have confusion between evolution time and mixing time.
Okay, so she not all two-dimensional experiment has mixing time. Only nosy and axi has mixing time. And mixing time is a fixed time, so it's not a variable. Toxi to some extent, but toxi is also spill out. The spill out is spill locked. It's also a mixing time, but there's a mixing in a physical sense, not in polarization. She's asking a very special question. I'm trying to answer her. I know she knows NMR better than me, but mixing time is a different domain. We'll discuss that when it comes to. But the experiment which I showed you, there's a provision of this is mixing time, right? But this mixing time is not a variable. It's a fixed time.
What happened?
Magic. That I'll tell you later. But this is not a variable time, it's a fixed time in which
We could talk about the sign or it is like itself.
no, we have everything is controlled. In NMR spectroscopy, everything is predictable. Think of it. If I never told you about vector diagram, you could have never understood where it goes. If I never told you about rotating frame of reference, you would never be able to see where these vectors are. And if you are not able to see vectors, you will not be able to give them a second pulse. So everything is predictable. If I never told you that C13 and proton and oxygen and nitrogen are in different frequency because of the galvanic ratio, and you can detect one in the presence of the other, you would have never known that can be done. So everything is coordinated. NMR spectroscopy is all about predictability. So much theory has been developed that it becomes predictable. You kindly have your tea and coffee because Professor T is absolutely impatient for that. She likes samosa very much. You know samosa, right?
Sambusa.
Can you explain what samosa is in theoretically? Yeah. I mean, think of someone who has never seen a samosa, maybe in a Caribbean island. sitting there and you need to give a lecture. How would you explain it?
Okay. Maybe I will start from what the person understands or what he doesn't understand.
About samosa.
So, most probably the person would have known the meat pie, something like that.
Feedback.
Yes, meat pie. So I said, meat pie is.
I think we need to do it quickly because chat and due date. So we need volunteers. Number of volunteers, men and girls of our. Okay.
Okay. So I start with meat pie from one side, from what the person knows, and samosa doesn't know samosa. So I talk about the origin. The meat pie is from the West, normally it's from the flour, chicken, beef, but samosa is similar. It's from the flour that has more spice, it's more spicy, and more creamy. That means the back.
Can you do that by the time they take the things? I just want to tell you how critical thinking works. Please. Consider someone who has never seen a samosa.
Okay.
आप समोसा खाइए.
Okay, if I have to draw a samosa, it looks like this. This is the shape, while meat pie is always like a pie, like this. So it is not the shape of the pie, but the basic principle is that they have similar covering, but the contents is different. That is, the content is different. The texture, this is often soft, while this is a little bit flaky or crispy. So, which is a little harder, but inside, which is the magic to me, is the spice. Because this one is oftentimes not spicy, while this is really spicy. So from the look, you can tell the difference. This one is mostly pie shape. This one is slightly triangular. And then this looks whitish, a little whitish brown. This is more brown. Then if you have the opportunity to taste, then this is more harder from the outside and spicy on the inside. This is softer on the outside, not really spicy on the inside.
So absolutely. Think of it that even if you don't understand NMR, you understand. That part of it. But for samosa, to be honest, for me, there's a lot of for instance, samosa of my favorite has a handle. Right? This is the handle. Honey.
One prof, it's a pleasure to be back to iccbs. I was here 2017.
I will share with you my samosa. I only take handle.
Okay.
So you can have your own samosa.
Thank you. All right, I'll see you later.
Yes.
Excuse me, sir. In this case, now you said we have. You said we have, this is for 1 crore. We have 400 experiment. And that's mean we have 400, this is 5. And we have also, maybe, about the F2 over here. That's it. How do we think about this experiment?
Your choice. Okay. So for simplicity, we are showing one peak. Imagine that if I am showing 100 peaks, we'll be very confused, right? So simplicity, I am showing in the spectrum of one proton. Okay, one proton. And this is one NMR spectrum, one experiment for the same proton. This is second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, 11, 12. And so many of them. As many experiment as you see the peaks. So one proton, which is not coupled with anything, assume that, This is the reason why singlet, right? So you bring it like this, you record FID, you get a spectrum. Okay? Then another experiment in which you bring 90 pulse, bring it to XY plane, and wait. Even it has moved from the Y, let's assume, a little bit away from the detector. Okay. You record FID. Third experiment, you give a little bit more time. It has moved little more away. Okay. You record FID is a different FID. And you record hundreds of these FIDs because you see it's actually moving like this, going from plus X to minus X, coming back to plus X, right? And you are recording this evolution through FIDs, recording so many FIDs. Okay. So this peak is obvious. This peak would be positive, and these peaks will be negative after some experiment. And then they will come back to positive side. And then again back to the negative side. And then come back to positive side. And come back to negative side also. So all these spectra which you have collected for one proton, if you put them together on plastic sheet, one after the other, infinite till the road. Okay? One spectrum, second spectrum, third spectrum, fourth spectrum, 200 spectrum, 300 spectrum, depending on evolution time. And now, if you just turn, let's say you go to 9, you turn like this, and you see your peak. You see all these peaks. These peaks will look like this, isn't it? Right? And these peaks are different from each other because of what? Yeah, because it's moving on XY plane. It's a sinusoidal function. Sinusoidal function, right? And if you see that, you say, good Lord, is evolving. And if I just convert that into a pseudo FID by making a line on top of it, I get something like this, right? And this is not a real FID. You have not recorded it by detector. You just constructed it on the basis of frequency spectra. And this represents evolution because of T1. You have already done one frequency because this is the frequency domain spectrum which you have seen. Now you do another Fourier transformation. And when you convert this T1 time FID, pseudo FID, you get another damn frequency. Because every time is converted, Fourier transformation will give you a frequency. So you get two frequencies. One because of detection time, and the other is because of evolution time. So you get two frequencies. Now I want to take you to a beautiful experiment which is my favorite. This is my personal favorite. And I keep repeating this experience of mine. Okay, so I was a MSc student. I came to its institute. This institute used to be a very small one, just few labs, and every student was required to give a seminar. So there were altogether 30, 35 students. And our teacher, Professor Dr. Rahman, he used to give us a list of topics. And he was traveling a lot like me. So he wanted everyone to give a lecture, a presentation, every student. We didn't have courses at that time. No courses, nothing, only research. What a wonderful time, huh? Okay, so I was a brand new student, came from university, and it was like my second, third day. And in the corridor in front of Professor Atta's room on first floor, a huge man, a student who was like 6, 7 feet high. He was the strongest among us. His name was Ajmal Nasir. And generally he was, he had this list and he had this wonderful sense of, he was like a very smart person. He knew exactly that this list of lecture for everyone, 35 lectures, supposed to be given by 35 students. You give some lectures, Professor Atta will be traveling again, he would forget. He will forget, and then, so the best way is that catch the weakest, okay, you have to give this lecture, right? 2, 3, 4, 5, by then Professor Atta was in England, and he never gave this lecture in 4 years of stay. He was always making weak people to give lecture. So I was walking, I used to have long hairs. Can you believe it? And I used to wear jeans also. So I was walking on the corridor. He caught me from the shoulder. I said, "Who are you?" I said, "I'm a new student." Okay, this institute has a great academic standards, and we want every student to give lectures. I thought he was a teacher. Later, I learned that he was a student. And he said, "Okay, now in order to improve your understanding and your academic stature and giving your topic, you have to give a lecture." So he gave me this energy equate. There was first number one in his own writing, Dr. Atta's writing. It was inadequate. And he said, "You have to give a lecture next week on this topic." And I said, what is this? He said, don't ask me questions. So, what is this? You're supposed to give a lecture, you're asking. I said, can you tell me what it is? He said, we don't spoon feed. We want students to learn by themselves. So I was a poor student with this word in front of me, and I didn't know what to do. So I went to the library. Finally, I figured out that right at that time, a new experiment was developed, inadequate, NMR spectroscopy, and inadequate was incredible natural abundance double quantum transfer experiments. Can you repeat it? Go read it. Inadequate. Incredible natural abundance double quantum transfer experiment. And in a week time, so I was in the library for literally 7 days, from morning to evening till late in the night, learning about inadequate. And so he said, okay, everybody was in the seminar room, same way you get to class, but you should, yeah, this was a seminar. And I presented shaky and all that. And even before the lecture, you came to me and you prepare yourself. I said, yes, I did. So can you give me some questions which I am supposed to ask you? And then I was a bit more clever. I said, no, okay. That you listen to my lecture and ask questions to yourself. I don't do that. So okay, so I presented this, and this was my first exposure to modern maths. I could have learned NMR when I was in MC. They're not so nice. And then Professor Tala, in everything there is a blessing. And he saw me, and once I completed my lecture presentation, it was a poorly understood presentation. What do you expect from someone who came from the university? And he said, when I went out, he said, you want me to write a book together with you? My first week in this institute, Ajmal Nasir gave me this topic. And I became the author of a book. Can you believe it? So I want to take you to this very interesting journey of me torturing and eventually rewarding. It's called Incredible Natural Abundance Double Quantum Transfer Experiment. You're okay with this? Okay, can you explain to me now what it is? Okay, so this technique was at the genesis. It was developed, and it's a beautiful technique. This is one of the most beautiful techniques, initially neglected, later because of all that, it came back. And this is a technique which provides you homonuclear coupling between carbon and carbon. Okay, so cozy, proton block, right? But organic chemists or even other chemists also, they're more interested in carbon framework. For them, carbon framework is the structure. Hydrogen are just put on it, The actual structure is carbon connectivity, isn't it? Carbon-carbon linkage. So someone thought, why don't we develop an experiment in which we should be able to see carbon-carbon coupling? It means carbon-13, carbon-13 coupling. It means having two carbon-13s together with each other, coupled to each other. Now, measure that the natural abundance of carbon-13 is only 1.1%. 99% is carbon-12. Having two carbon-13s together is a nightmare. having two carbon 13s together, the possibility is only 0.011%. So you're trying to detect a spectrum of a weaker magnet like carbon 13, 1/4 of the gyre magnetic ratio. And for that signal, which is because of two carbon 13s adjacent to each other, nightmare. So this is the reason why someone said incredible natural abundance, incredibly low natural abundance of having two C13s together. Okay, and this was this experiment. If we can have coupling between C13 and C13, if we can somehow detect that, you don't create a structure indirectly between proton-proton. You create a structure directly by connecting carbon 13s together with each other. So that was the beginning of an extremely exciting experiment, which is now used very because people have figured out how to make it more sensitive. Because I think that's what that is. So let me read it through. Ultimately, in extremely insensitive technique, okay? Incredibly low natural abundance of having two C13s together. Chances of finding two C13 nuclei connected to one each another is 0.1 in 10,000. 1 in 10,000, not molecule, but 1 in 10,000 of those which have C13. Okay. And to detect a weak interaction, it is necessary to suppress the 100 times stronger signal for molecule which contain only an isolated C13 rather than two adjacent C13. Okay. I am a C13. Okay. In a big chain of carbons. And I don't have a C13 neighbor. It's normal, you know. I know that a very insensitive, not by nature, it's only because of galvanic ratio. Okay, and then low galvanic ratio and all that. And then another molecule in which I have a carbon 13 neighbor. By chance. The possibility of an isolated C13 is 99% more than having C13 next to C13. Okay? So if you detect one-dimensional NMR spectrum, it's so easy, C13. You have C13 given XY plane, you detect it. With decoupling, you get one single spectrum. Okay? Now, those C13s, which have a neighbor as a C13, very low. You will never be able to detect them unless you remove this strong C13 signal because of isolated C13. Okay. What was observed, Gunther has observed that if you have a very high concentration of sample, if you have tons of sample, you are successfully able to solve that. This C13 spectrum has something like this, you know. So he saw what he saw was that in the C13 spectrum of a highly concentrated, you can see that? You see only Samosa, right?
Why do we care about
for airborne safety.
Yeah, that is
It puts put in fine. How?
okay. Honey, you look very confused. What is it? Okay. So, how many carbon signals? Two or how many? How many, brother? You saw this. He saw something like this and he was so curious. Remember, curiosity is the mother of invention. You have to be curious. You have to be super curious. Not about each other, but about. Okay, so this belongs to this, and this belongs to this. Okay? Find two decoupled carbons again. What was it? He said, what is this? Small shoulders. And initially he called that a satellite peak. Satellite peak. Lights. Okay, so, and then he thought of it. He said, okay, these C13, CH2, CH2, CH3, carbon 13 are can be C13. There is slight possibility in which both of them are C13. Isn't it? Right? And when this is a C13 and this is also a C13, it will split. Okay? It will appear as what? Like it will appear as what? Doublet. So he said, I would be able to see this if I isn't it? He would only be able to see this when he removed this 100 times stronger isolated C13 signal. How would he do that? Think of it. Now, this is a very simple molecule. But if you have like 200 C13 and if you are able to see these satellites with each other, you can put them together, you get a whole skeleton. Right?
It could be noise.
Yeah, that's a important observation. It can be noise. But if this appear exactly in the same position consistently, then it's not a noise, it's a signal. And that signal, right away, to the smart man, he could understood that actually representing this very rare possibility of having two C13s together. And therefore it appear as a doublet. Okay. So there was a question. How to detect them? How to detect this absolutely small satellite signal in the presence of a very strong isolated C13. And that has given to the birth of two-dimensional experiment. Later, it was one-dimensional to begin with. And you see, okay, so you okay with the 90x pulse? Your favorite 90x pulse? Yeah, you have to convert longitudinal magnetization to XY plane. Okay. And then this carbon, let's say assume that this is this carbon. Okay. This will split into
carbon or by proton?
no proton.
No,
Carbon. It's a fully decoupled spectrum. Thank you. Every question makes sense. So it will split into doublet. But there is also a signal which is because of C13. Strong signal. Isolated C13. Right? Where there is no couple, there is no neighboring C13. Okay? Understood? This thing represents this doublet, this one, and this one represent this small little possibility where there is a C13 next to a C13. This big thing, and you can't make it bigger than that, your book would full. Represent isolated C13. How would you remove it? That is the beauty of NMR spectroscopy. Now, you wait for a while, you see this doublet going to antiphase, spreading. You give a 90x pulse, you bring this strong isolated signal to here, you remove it, right? You remove this big small signal, you bring it to the Z, and what you have on the XY plate? Only the doublet, isn't it? Absolutely beautiful. Excites you so much, You feel so happy. You feel so elated. It make you happy. You don't see. I don't see. I is happy. No. Okay, brother. If you understand that, you almost understand the samosa which was presented to me. I was thinking if I sit in Caribbean, and if I've been explained like this nicely, what I would eventually make. Yes, honey.
Wait, I have to. No,
What is this?
the carbon
Yeah, doublet. It's a doublet, right? Remember, it's a doublet for that carbon which has a neighbor as a carbon. Right? Okay.
I think it's one of them. Why you want only one cup? 90 bucks for in this situation. Why you make it only one paper? What I think it will be here and it will be here. I have proper allow that.
No, but this is X. If you give a pulse, what will go? No. If you give a pulse from here, nothing will happen with them.
Only one.
Yeah. Khatam. Isn't it? Are you happy with this? Yeah.
I would
You
have the
happy?
same question to ask.
Now you happy? What a beautiful experiment. Think of it. There is absolutely no technique in which you can play like this. It's a play. Feel like you are playing with the toys, in which now what you have done is that you have removed this very, very strong pulse, very, very strong magnetization, which represent single C13 without any neighbor to Z. If you place it to the Z, you don't see it. You only see when it exists on XY plane. And in that case, you see like this. So you see, this is number one. Number one is connected to number two. Number two is connected to number three. Number three is connected to number four. What a beauty. What a beauty that you constructed this whole molecule by removing the strong isolated C13P by a trick which you have developed. Okay? That is the beauty of it. That make you so happy because you can play with it. Thank you. Thank you very much. Yes, sir.
सर ये सवाल ये था कि
आप सवाल कीजिए।
जब हम NMR को स्टडी करते हैं तो हम कहते हैं कि ऑड नंबर ऑफ न्यूट्रॉन हो या ऑड नंबर ऑफ प्रोटॉन हो या बोथ, तो वो न्यूक्लियाई एक्टिव होता है। और हम अभी पढ़ रहे थे HNMR, तो इसी तरह हम न्यूट्रॉन का क्यों नहीं इफेक्ट देखते?
Okay, so see what he's trying to ask is that we call this proton NMR. So it's confused, why not neutron NMR? Okay, so can you remember that it has nothing to do with neutron or proton. You don't detect proton or neutron. You detect the nucleus spin. And this condition that odd number of neutron and odd number of this makes this nucleus spin NMR active. Okay. So when I say proton NMR spectrum, it's just a hydrogen NMR spectrum. And it's confusing. To be honest, someone should really correct it at some time. We all use proton NMR because hydrogen has only one proton in the nucleus, so we start calling it a proton NMR. It's actually not proton. We're doing nothing with proton. It's a nuclear spin of hydrogen. There should be hydrogen NMR spectroscopy. Okay?
So my question is related to 1/4J. Like this is a coupling constant. So every carbon.
Okay, so here we're talking about coupling of C13 and C13, right? Is J. So J in this case is translated into time. J is time in this case, not in hertz. Remember, everything is in time domain. Our NMR spectrum eventually converted into frequency. Currently, this is time. You don't give J as a gap. You can only give time as a gap, right? So J is actually time, and we write it because it's just it means that this time is required in order to detect the coupling. Yes, sir.
What's the symbol of this to make like I want to for my own carbon any of like
You write inadequate. Is asking if I need to have carbon-carbon 13 coupling inadequate. what I need to do is it inadequate. Like you request for cozy, nosy, you can do that also. Problem with inadequate is that it's still a very insensitive technique. You know, remember the carbon 13 is also already a nightmare. Having two C13s together is an even more or greater nightmare. You need to have more samples. The NMR time would be more, going to be more skinning and all that. And this is the reason they discourage it. Okay, but the fact is that it's a very useful experiment. And it's an excellent example to demonstrate the power of NMR. Yes. So you can go for inadequate.
Can we apply the same thing about the nitrogen also without nitrogen?
Absolutely. If you put nitrogen together and you want to see nitrogen coupling, like in many compounds, you would be able to see exactly the same thing because nitrogen isolated nitrogen 15, the possibility is even less. But this has not been developed for nitrogen because nitrogen is terribly bad. Nitrogen is 10 times lower carbon integration than proton is about 300 times lower natural abundance than carbon 13. So it's 0.035 or something like that.
What the fuck is integrate? What information can I give? Okay, about the need of chemical.
The actual purpose of this is to make you happy. So the purpose of this experiment is to eventually create a carbon framework. I'll show you the experiment. Thank you. Okay, sorry, how much it costs to analyze one sample using NMR? Cost, it depends on the use of deuterium. You know, some deuterated solvents are just so cheap. Like CTCl3 is very cheap, only one deuterium. If you ask for DMSO, there's 6 deuterium. So DMSO is more expensive. If you want your NMR to be recorded in DMSO, they'll charge you more money. Okay. And also it depends on NMR machine. We want NMR machine like superconducting 600 because of the cost of the machine. The time of the machine is also costly. These are exactly like you're traveling in Ikea or in Mercedes. Eventually, at the end of the day, they'll charge you more, right? And so this is okay. And then, what was the question?
So I have another mistake.
Purpose is to build structure, okay. So, this is a small molecule, but you can construct the whole C13 for a large molecule also. There is an example which is currently hidden. Anyway, any more question?
Thank you very much for the lecture today. I'm beginning to experience a shift in the way I look at NMR and look at the chemical structure of compound. And I want to be sure that this shift is the right one. I'm beginning to see the molecules not as bricks being joined together, but as pores from each of the atoms or the nuclei. And that pores, the interaction between the pores becomes like a wave. And it is that wave that is being recorded by the machines as the peak, and I'm beginning to have.
Yeah, it is a beautiful description, to be honest. We in NMR spectroscopy don't see them as elements. We see them as magnets. The magnets are poles. And then you also know that magnets affect magnets, right? So the effect of one magnet with the other magnet is what is you're trying to detect. If proton magnet is detected, it becomes cozy. If proton-carbon magnets were detected, they become HSQC. If you see two magnets far away from each other interacting with each other in space, it's nosy. So you're right. But after this description, I have started seeing samosa in a different perspective also. Thank you.